Hello, my name is Nick Heppert, and today I want to talk about my joint work with Toki, Brand, Claire, and Jet on how we use vector graphs to track articulate objects independent of their category. While many recent works made great progress in tracking articulate objects on a category level, most of these approaches suffer when an object instance does not follow the assumed category-specific kinematics. For instance, a laptop or sunglasses are pretty well-defined categories. They both always have the same kinematics. But how to define a category for more complex objects like this piece of furniture shown in the GIF? Here, initially it seems like the object has 4 individual prismatic drawers, but as soon as the person interacts with the object, we discover it's only a single revolute door. We therefore argue, as articulate objects vary greatly in their appearance, geometry, and kinematics, to track all objects a robot could encounter in the wild, we need methods that do not make fixed assumptions about an object category, but leverage temporal information to be more flexible during inference. Or, in other words, given only a sequence of an interaction, methods should be able to detect and track individual parts of the object as well as their relation without any additional information, such as a category prime. To tackle this problem, we propose the following pipeline. As input, we only have a sequence of raw output RGB-D images without, compared to other work, any object or part segmentation available. Our pipeline outputs a pose for each detected part, as well as the articulation model between parts. To start, we feed each subsequent pair of images through an autoencoder, which produces a pixel-level dense motion map. We then use this feature map to cluster pixels together that move coherently and thus are deemed to belong to the same object part. This process could be considered a single time-step detector and produces individual detections for each subsequent pair of images in our input sequence. After processing the full sequence, we aggregate the detected parts in our cluster matching step. This will give us a part trajectory for each part over the entire input sequence. Last, we construct a vector graph based on these trajectories that infers the articulation mechanism as well as refines the trajectories to be more consistent with the inferred mechanism. The final articulation mechanism consists of the time-invariant joint parameters and the time-varying joint states. And now we'll go through each component in more detail. First, the part tracking module. Compared to recent work such as Captra, our model detects and tracks arbitrary amount of part independent of the category assumption. In the first substep, our single-step detector takes 2 consecutive RGB-D images as input and predicts the following pixel-level motion features. An importance value, which ranges from 0 to 1, where 1 represents pixels that are closest to the part center. The elicitation is shown on the right here. We also predict each pixel's respective part center in the camera frame, which is again shown on the right. And last, we predict a delta pause describing how that part moved between 2 time steps. But for clarity, we omitted the visualization of this. Based on these predictions, we cluster pixels together based on the current center as well as the transformed center at the next time step. We can easily transform the center by applying the predicted delta pose to the current center. Then within each cluster, each pixel then votes for the final part center and the delta pose. After detecting parts in each subsequent image pair, we will match these parts over time for the full sequence using the nearest neighbors algorithm and retrieve a raw trajectory for each part. For now, we only consider objects with 1 fixed base part and 1 moving part. In the figure on the bottom left, you can observe how we successfully extracted the base part trajectory, essentially not moving, and on the bottom right, the moving part trajectory for the door in this example. Given these raw part trajectories consisting of part centers and delta poses over time, of the fixed base part A and moving part B, we'll use a vector graph to infer the smooth part trajectories. In our vector graph, we denote the part poses by XA on the top row and XB on the bottom row from time step 1 to T. Additionally, we name the time-invariant joint parameters nu and additionally transform T on the left. Finally, we denote the time-varying joint states Q, which also ranges from time step 1 to 2 in the middle. To bypass potential mixed integer programming for making a discrete decision of our joint type, we'll use a twist formulation on our vector graph. Similar to the recent student work, this allows us to continuously optimize for rigid, prismatic, revolute, and helical joints without imposing any discrete choice. For this, we will simply multiply the time-varying joint parameter QAB with the time-invariant base twist nuAB, and through the exponential map, we get the transformation between the base part and the moving part at a specific time step T. We then can use off-the-shelf vector graph optimization libraries to solve the optimization problem and infer the articulation mechanism. In this visualization, you can see the results of the linear component of the inferred mechanism at the moving part center, for the moving part center over time. Last, we also introduce a new evaluation metric that helps us to quantify how efficiently a robot or a compliant controller would move the object based on the predicted articulation model. To interact with an object, a robot does not need to know whether the object has a prismatic or revolute joint or where each axis lies in space. Rather, the robot just needs to know in which direction to push or pull. Our metric exactly captures that. Given at the specific point, for example, the handle of a door, we calculate the dot product between the linear component of the ground truth calculation mechanism and of the predict mechanism. Here, the ground truth component is orange and the predict component is blue. For full evaluation, we integrate over the ground truth joint state range for the object. The resulting value ranges from 0 to 1, where 1 is the best possible value and 0 is the worst. This is the metric we will report in the following slides for our experiments. Here we show qualitative examples for the factor graph compared to an also category agnostic baseline by Sturm et al. This method calculates the likelihood of all joint types and makes a discrete decision instead of using a continuous representation for all joints as in our factor graph estimation. Both methods use the same path trajectories as input tracked by our method. On this slide, we present results when trying to track an object with revolute joints. The errors are the linear component of the underlying articulation mechanism. This is the same as the previously mentioned linear component that is used to calculate our metric. We report the value of our metric in the bottom left of each animation. As you can see, overall, the factor graph performs better on all of these examples. The bottom left figure contains an example where the baseline falsely classified the joint as prismatic, and thus the prediction error is quite high. The linear component does not change the direction depending on the opening state of the door. Our factor graph approach does not suffer from this problem, as it does not have to make a discrete choice of the joint type. On this slide, you can see the same type of visualization, but for objects with a prismatic joint. As for the previous example, our factor graph performs significantly better than the baseline, except for the example on the right. Here, the factor graph overestimated the rotation component, whereas Sturm's method successfully classified the joint type as prismatic and was able to use that bias to compensate tracking errors. This wraps up my presentation. Feel free to reach out via the email shown if you have any questions.